Okay, finally we are at in-class exercise 3 for alkenes. The first question is on distinguishing tests, which is a very common question you'll be asked in exams. Especially in JC2, where there are different functional group present between 2 or 3 or even 4 unknowns, and then you are supposed to use a simple chemical test. So the key word here you might want to take note of is actually the simple chemical test. Simple chemical test here refers to basic test tube chemistry, no complicated setups, definitely no reflux, no distillation. Yeah, so it basically just involves a test tube containing your unknowns, and then you add the reagent in dropwise, and then you observe whether there's a color change. Okay, the most you could do is actually to heat it in a water bath and to warm it in a water bath, and then to check whether there's any color change. That's the most you can do. So any reaction which involve like complicated setups such as reflux, distillation, etc., right, they shouldn't be used. Okay, so please remember this, because once you are using reactions involving very complicated setup, then immediately it will not be read. Yeah, it will be deemed as incorrect. Yeah, so the keyword is simple chemical test. Okay, so for 1A, you're supposed to distinguish between 2-methyl-but-2-ene and 2-methyl-butanes. You realize the difference between them is the presence of a CC double bond in the but-2-ene, and then 2-methyl-butane is actually an alkane. Yeah, so this for 1A is basically just a test for unsaturation. Okay, so any test which allows you to test for unsaturation works. So the simplest example you can use is actually aqueous bromine. Yeah, so when you add aqueous bromine to 2-methyl-but-2-ene, you expect yellow-orange aqueous bromine to decolorize. And then for 2-methyl-butane, it will remain yellow-orange. Yeah, so remember that when you are writing the results for distinguishing test, you're not supposed to write things like, it didn't change or nothing happens. Okay, so you are supposed to indicate the color of the reagent which you have added. So in this case, aqueous bromine, for the alkenes, it will decolorize. For 2-methyl-butane, it will remains as yellow-orange. Okay, and then moving on to the next part. Okay, so some of you might ask, is there more than one answer? Yeah, of course there are more than one answer. Any test for unsaturation works here. If you are happy with adding potassium permanganate acidified with H2SO4, that works as well. So for 2-methyl-but-2-ene, you will get decolorization of purple KMnO4. 2-methyl-butane remains as purple. Okay, so there are more than one answer to distinguishing test. So you guys do not really need to worry about missing some answers out, or you're supposed to write a lot of answers. No, usually just one reagent which clearly distinguish between the two. Okay, so for 1B, you have cyclopentene versus cyclopenta-1,3-diene. Okay, so actually this is simply just cyclopentadiene. Okay, how do you distinguish between the two, since both of them have alkenes or CC double bond as part of their functional group? You might realize that if you subject both to oxidative cleavage condition, so which is what I mentioned earlier on, KMnO4 acidified with H2SO4, and then you warm it in a water bath, you realize that both undergo oxidative cleavage. So cyclopentene will cleave here, and then cyclopenta-1,3-diene will actually cleave over here and here. Okay, so this particular portion over here, right, the first product you get is actually the ethane diol acid, but as you are aware, ethane diol acid will be further oxidized to give you 2 equivalent of carbon dioxide gas. Yeah, so you could actually test for the presence of CO2 by bubbling the content into lime water. So you'll realize it will give a white PBT in lime water. Okay, or if you are sharp enough, you could actually realize some form of effervescence being evolved. Yeah, but just make sure that when you warm it in the water bath, the temperature is not too high as to cause the water to boil. Okay, so that in that case, you can actually observe the effervescence of CO2. But sometimes if the concentration of the alkenes is too low, right? The amount of CO2 being released is also on the low side, so you might not really observe the effervescence as per the normal effervescence you observe when you add sodium carbonate solution to acid. Alright, so we're going to move on to the next question, which is actually question 2 on structural elucidation. Okay, so if you recall your in-class exercise 2, that there are 3 structural elucidation questions. So, and we have talked about some of the strategies you can use to solve elucidation problems. So we will use the same strategy to work on question 2. So for question 2, you were told that you have an unknown X, which is an optically active compound. Usually the word optically active tells you that the unknown is asymmetrical. I mean, in most cases for H2, you will tend to conclude that it has a chiral center, has at least one chiral center. Okay, that's for H2 but as some of you might be aware, a molecule being optically active need not just have a chiral center. You can have a chiral axis or chiral plane, so we are not going to do that. So we just look at it from the simplest perspective. So probably have at least one chiral center. With this particular formula, C10H16, we can actually calculate the degree of unsaturation. Okay, so if you want to recall how do you calculate the degree of unsaturation, we look at the maximum number of H that a 10 carbon can have. So that will be 22H based on 2n plus 2. So that will be 22 minus 16 divided by 2. So in this case, I'm going to get 3. So that means that the unknown X has 3 double bond equivalents. 3 double bond equivalents can mean that you really have 3 CC double bond, or it could be CO, but in this case there's only C and H, so 3 CC double bond. Or you can have 1 ring, 2 CC double bond, or 2 rings, 1 CC double bond, or even 3 rings, or even 1 triple bond and 1 ring. So you can have a lot of combination. But as and because you have a lot of combination, you might think that calculating degree of saturation is kind of useless. It need not be the case, because if you scrutinize the remaining clue given to you, it will be quite obvious that our unknown has 2 CC double bond and 1 ring. Okay, so how do we conclude that? Let's look at the first paragraph, or rather the first line. You were told that when X reacts with HBr gas, it forms this particular compound. So if you take a difference between the two formula, right, you realize from here that 2HBr has been added. Yeah. So when you are writing out your deduction, right, make sure you tabulate your observation, or maybe not observation, but the information given to you. So you can have info, and then you can have deduction. Okay, so this particular information, point number 1, right? This particular information, right? It actually tells you that my unknown X contains 2 CC double bond, and then electrophilic addition occurs, and then yeah, that's about it. And then if you couple with a degree of unsaturation, because you know that it contains 2 CC double bond, then you will know that the remaining 1 degree of unsaturation must be due to a ring. Okay, and of course, if you want, you can incorporate this optically active part in, okay, which I didn't write it down. So you can actually put has at least 1 chiral center into this as part of your deduction. Okay, I didn't write it out earlier on because, as I said, I'm actually the key focus in this review is really to teach you how to get your answer rather than how to draft your answer. Okay, the thought process is actually more important here, because I think writing out the proper information deduction kind of answers, you have seen that in your tutorial solutions. Okay, and then of course the second clue they gave you was that when treated with concentrated KMnO4 with sulfuric acid, X gives Z and CO2. So the most important details here is that X actually gives Z and CO2. So if we were to write, just to calculate the number of carbon in Z, so that will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So you realize that there are 9 carbon in total. Sorry, there's one carbon missing. So the carbon missing is actually CO2. So the CO2 is actually carbon number 10. And then the structure of Z is given to you. So the question is, they ask you to deduce. So the command word they use is deduced. So if you're supposed to deduce, you need to explain how you arrive at your answers. So the explanation in arriving at answers includes the tabulation as well. Okay. From the info, what kind of deduction are you going to make? Yeah. So for the oxidative cleavage, you have to write it in as well. So you have to incorporate the part that oxidative cleavage occurs. Oxidative cleavage occurs. Okay. And then from the position of the CO double bond, you can actually conclude the original structure. What are the potential groups that are linked together? Okay, so here in order for us to look at the structure here as well as the deduction, I'm going to shift my deduction to somewhere at this region so that you can take a look. But of course, in actual fact, you have to write out your deduction over here. Okay, so here I'm going to propose some possible linkage. Okay, so the potential position of the CC double bond, the original CC double bond. Okay, let's say if you want it to be between C2 and C8, yep, that will mean that C7 and C10 will give me the terminal alkene, and then C2 and C8 will be the cyclic structure with the double bond. Okay, so between C2 and C8, let's do a quick count. 1, 2, 3, 4, 5. So that will be a 5-membered ring. Okay, and then with a terminal alkene between C7 and C10. Okay, so this is one possibility. So this is possibility 1. We can have possibility 2 over here. Okay, so what's possibility 2? We can have instead of C2 C8, we can have C2 C7, and that actually means that the CC double will be between C8 and C10. Okay, so that's possibility number 2. And then we can also have possibilities number 3. That would mean that my CC double will be between C8 and C7. Yeah, so if we do a quick count, that will be a 4-membered ring, and then my terminal alkene will be between C2 and C10. Okay, so 3 possibilities. With the 3 possibilities, we'll try to sketch out the structure below. So let's try to do it. So number 1, the first possibility. Earlier on we said it's a 5-membered ring, so we try to sketch out a 5-membered ring here. And then between C2 and C8, there's a CC double bond. So if we label this as 2, this will be 8. And then 8 has a methyl group. That's number 9 over here. Okay, so that's number 9. And then we just going to number backwards. So that will be 5, 4, and then 3. And then 2 is bonded to another methyl group as well. Okay, and then for carbon number 5, I'm going to have 6, 7. So this is 6, this is 7. And then there will be a double bond here. Okay, so this will be number 10. Okay, which is the terminal alkene. Okay, and then let's try to draw a structure for possibility 2. So we have a CC double bond between carbon 2 and carbon 7. That will be a 1, 2, 3, 4, 5, 6 membered ring. So it will be a 6-membered ring over here. So between carbon 2 and carbon 7. So if we number it backwards, that will be 6, 5, 4, and then 3, and then 2. 2 will have a methyl group, so that's bonded to carbon number 1. Then carbon number 7. Okay, sorry, carbon number 5. There will be a group bonded to 8 and 9, so that will be 8, and then 9. And then there's a terminal alkene bonded to carbon number 8. So this is a terminal alkene. So this is carbon number 10. Yeah. So this will be the structure for Z. And then if you recall, we need to have a chiral center over here. So because it's optically active, into the chiral center. So maybe we should also try to indicate the chiral center. So this is likely to be the chiral center, and this is likely to be the chiral center as well. Okay. Or rather, this is the chiral center. Yeah. okay, because it is asymmetrical. Okay, and then finally we'll try to do for the third possibility. So we're going to do it below over here. So again, that's between carbon 8 and 7. So that will be a 4-membered ring. Okay, so since it's a 4-membered ring, we're just going to draw a square. Okay, going to draw a square over here. So that will be between carbon 7 and 8. Okay, and then 8 will be, you have a carbon number 9 as a methyl group. Okay, and then after that, there you have 5, 6, 7. So carbon number 5, you have 4, 3, 2, 1. So this is 4, 3, 2, 1. So carbon number 2, you have a CC double bond, which give rise to the terminal alkene. So that will be the CC double bond over here. So this will be carbon number 10. Okay, and yep, that's about it. And I hope you can understand the thought process in getting the answer, because there are some details which I've missed out, especially in the deduction part, like how to write out the deduction. But briefly, for deduction, you need to incorporate the potential structural features. So for example, does it have a chiral center? Does it have 2 CC double bond, 1 CC double bond? And then you also need to indicate the mechanism of the reaction or the types of reaction. Is it electrophilic addition? Is it oxidative cleavage? Or for the case of arenes, is it side chain oxidation, etc.? Okay, so there's a final part to this particular question. You're supposed to write a balance equation for the reaction between X to give Z and CO2. So again, the balance equation is not a redox equation in this case. So X will be C10 H16, and then you add in the appropriate number of oxygens. So your product is actually Z. So for Z, if you do a quick calculation, there are 4 oxygens, 3 degrees of saturation. So that will be C9. 3 degrees of saturation means 2n plus 2, 20. 20 minus 6, so it will be H14. And then O4 plus there's a CO2, not to forget. And then the number of hydrogens. So you have 16H on the left, you have 14H on the right. So I will have an extra H2O here. So if you do a quick count, there will be 7 oxygen. Okay, so this will be the balance equation. Okay, so I hope you find the review useful, and look out for further videos on other in-class exercises.